Hi all, so welcome to the discussion on electromagnetic waves. So in this lecture, I'll be discussing about the propagation of electromagnetic wave in linear media. So before going to the linear media, so first we can just review what we have discussed till now. So what we have discussed is the electromagnetic wave in vacuum. So in the case of electromagnetic wave in vacuum, we have for equation, the Maxwell's equation, del dot E becomes 0. Del cross, okay, better we'll write del dot B. We'll use the same pattern. Del dot B equals 0. Del cross E become minus dou B by dot T. And del cross B is mu 0 epsilon 0 dou E by dot T. So in case of vacuum, rho is 0 and J was 0. Okay. So these are the Maxwell's equation for the electric field and magnetic field in vacuum. So from this we can derive the three-dimensional wave equation. So those are del square E equal mu 0 epsilon 0 dou square E by dot T square, and del square B equal mu 0 epsilon 0 dou square B by dot T square. So this is the three-dimensional wave equations from which we can identify this mu 0 epsilon 0 is nothing but uh, 1 upon speed square. Okay, and we have found that this the speed, the corresponding speed of the electromagnetic wave, okay, that would be equal to c. It is 1 by root mu 0 epsilon 0 would give approximately 3 into 10 raised to 8 meter per second. So that is what we have seen in case of vacuum. And the energy density of electromagnetic wave is simply written as half epsilon 0 E0 square, and the intensity is written to be half epsilon 0 C times E0 square. Okay, so these are the things we have discussed in the case of electromagnetic wave in vacuum. So next we can see what would happen when you're going to, sorry. Okay, so next we can see what will happen if you're going to the linear media. So again, in the case of linear media also, we are assuming it's a source-free region. So consider a linear media with no source. So again, the free charge density is taken to be 0, and the free current density is taken to be 0. So there may be bound charges, and there may be the bound currents as well. Okay, but there will not be any free charges and free current. Okay, so if that is the case, then your Maxwell's equations would be del dot D equals 0, del dot B equals 0, and del cross E become minus dou B by dou T, and del cross B equal, sorry, del cross H equal dou D by dou T. Okay, so again, okay, sorry, this is not for linear media, this is for a media. So better we can write a media or a material, a dielectric material. So for a dielectric media, we can write this way. Okay, now when you're going to the linear media, what would happen? So for linear media, Again with rho f is 0 and jf is 0, what would happen? We can write d as epsilon times E. Now what is d here? Here d is epsilon 0 E plus P. And what is h? H is B by mu 0 minus M. In case of linear media, what happens is d become epsilon E and B become mu times H. Okay, so this is a very important result. So in case of linear media, electric displacement can be written as epsilon times E, where epsilon is called the absolute permittivity, and B can be written as mu times H, or H can be written as B by mu, where mu is called the absolute permeability. So then we can rewrite our Maxwell's equations. So our Maxwell's equation del dot D can be written as del dot E equal 0, and del dot B equal to 0 will remain same, and del cross E equal to minus dot B by dot T will also remain same, and del cross H can be written as B by mu, so it can be written as del cross B divided by mu. Mu can be taken to the right side, and D can be written as epsilon E, so del cross B can be mu epsilon dot E by dot T. Now if you compare this set of equation, the Maxwell's equations in vacuum, and as well as the Maxwell's equation in linear medium, they have the same structure. You just look at this, it is having the same structure. Only difference is the mu 0 is replaced with mu and epsilon 0 is replaced with epsilon. That is the only difference. Then what would be the corresponding three-dimensional wave equation? So there is no need to derive it. You can directly write. So the three-dimensional wave equation would be del square E equal mu epsilon dou square E by dot T square, and therefore the speed of the electromagnetic wave would be 1 by root mu epsilon. So speed of the electromagnetic wave in linear media would be simply 1 by root mu epsilon. And del square B will also satisfy the same equation. If you want, you can derive it. Okay, I'm not going to derive it. So I'm just writing from this analogy. So the speed of the electromagnetic wave simply 1 by root mu epsilon. And what would be the energy density? So the energy density of the electromagnetic wave would be can be simply written as half epsilon E0 square. So you have to just replace epsilon 0 with epsilon. So the energy density would be simply become half epsilon E0 square, or it is more correctly the time average of energy density. So better use this symbol. And what would be the intensity? The intensity of the electromagnetic wave would be half epsilon V E0 square. Okay, so in the earlier case, in the case of vacuum, I use C, but in case of linear media, instead of C, we have to use V. Okay, so which would be greater? The C would be greater compared to V. Okay, so how will you prove it? Okay, so better we can define a new quantity called refractive index. So refractive index N is defined to be C by V. The speed of light in vacuum divided by speed of light in the medium. So that is the refractive index of that particular medium. So C is 1 by root mu 0 epsilon 0, and V is 1 by root mu times epsilon. So mu is nothing but mu 0 times mu r, and epsilon is epsilon 0 times epsilon r. So if you substitute it, then what you will get is it will become root of mu r epsilon r. Now the mu r is called the relative permeability and epsilon r is called relative permittivity. And for most of the material, mu r is approximately 1. So therefore refractive index can be approximated as square root of epsilon r. So for most of the material, the refractive index is simply square root of epsilon r, and epsilon r is always greater than 1. So epsilon r always greater than 1 means the speed of light in the media would be lesser compared to the speed of light in vacuum. Okay, so there is a one way of explaining it, or there are other ways also, because if you just compare this two quantity, this mu and epsilon would be, the product of mu and epsilon would be always greater than mu 0 and epsilon 0. So therefore the speed of light in media would be lesser compared to the speed of light in vacuum. So this would be okay, what we can write is would be always greater than 1. Therefore C would be greater than B. Okay, so that's all about the propagation of electromagnetic wave in linear media. So in linear media, it behaves, or it obeys all the properties of electromagnetic wave in vacuum. The only thing you have to do is you have to just replace mu 0 with mu and epsilon 0 with epsilon. All the remaining mathematics, all the remaining physics are same. It is what we can call it as the transverse nature of the electromagnetic wave, the relation between the electric field, magnetic field, and the propagation vector, all everything are the same here. So if you look at the expression for the magnetic field, the magnetic field vector of electromagnetic wave, we can write as k cross E by omega. And if you just look at the magnitude of V0, it would be equal to E0 k by omega, or it become omega by k becomes the speed of light in that medium, that would be E V. Okay, so this kind of changes would come. Otherwise all the structures are same. The both all the electric field, the direction of propagation, magnetic field would be in mutually perpendicular direction, and the electric field is transverse. So if or we can write as k dot E would be 0 and k dot B would be 0. That is, there is no electric field and magnetic field along the direction of propagation. So the electromagnetic wave is transverse. So it obeys the transversality condition, and the direction of B can be got from this expression. And what about the Poynting vector? The Poynting vector is usually we write E cross B by mu 0. So here we have to write E cross B by mu. So these kind of small changes would be there. Otherwise, it obeys all the properties, all the behavior of the normal electromagnetic wave in vacuum. We have to just replace mu 0 with mu and epsilon 0 with epsilon, and C with V. Okay, so the electromagnetic wave in vacuum electromagnetic wave in linear media. So what are the differences? The C has to replace with V, and epsilon 0 has to replace with epsilon, and mu 0 has to replace with mu. So these are the only three differences. So all others things are same. Even the structure, everything, the mathematical structure of the energy density, the momentum density, the Poynting vector, all the structures are same. So only wherever the C epsilon 0 mu 0 comes in case of electromagnetic wave in vacuum, that has to be replaced with V epsilon and mu. So that is the only thing you have to remember. All transverse nature, and the same phase of the electric field and magnetic field is delta E equal to delta B. All these aspects are same for electromagnetic wave in vacuum and as well as in linear medium. Okay, so we have almost completed the discussion of electromagnetic and linear media. So we can stop the discussion with one particular point. I think better we can discuss in the next lecture, because in the next lecture we'll be discussing about the reflection and transmission of electromagnetic wave. So in order to discuss the reflection transmission of any wave, we need boundary conditions. So that we have already seen while we are discussing the phenomena of reflection transmission for wave in a string. So similarly, for electromagnetic wave, in order to study its reflection transmission, we need the boundary condition. So in the next class, we'll be discussing about the boundary condition, and thereafter we'll complete our discussion about the reflection transmission of electromagnetic wave at normal incidence. Okay, so for the time being, this is enough for us. Okay, we have completed the discussion of the propagation of electromagnetic wave in linear media. So the linear media and vacuum, the propagation is same. The electromagnetic wave is transverse. The both electric field and magnetic field are of same phase. Okay, the electric field, magnetic field direction of propagation are mutually perpendicular, and they are connected in this way. The B is K cross E by omega. The only difference is its speed. The speed of E electromagnetic wave in linear media would be slightly lesser compared to the speed of EM wave in vacuum. So that is the only difference. So compare accordingly, there will be some changes in the expression for the energy density, the intensity. Okay, this expression for the energy density we have talked about. So instead of epsilon 0, we have used epsilon, and intensity is this expression. So these are the only the changes that we have to consider. Apart from that, all the remaining physics are same. Okay. So see you in the next class. So the next class possibly will be the last lecture of this chapter, the electromagnetic wave, and as well as this paper. Okay. So thanks for watching. See you in the next class. Bye.